Thank you. Thank you very much for the introduction. It's a pleasure for me being here. I have to admit, first time being at ETH Zurich. If I would have the chance again, I would have arrived here much earlier. It's very impressive to see the centrifuge and whatever. It's really top-notch technology and scientific approach. Anyway, I only have 25 minutes, and it was kind of hard for me to pick whatever technology. So since I haven't been here, I was not so familiar. I apologize. I picked pipe tracking and vertical shaft sinking machines. But we have a much wider product range, which I want to show you also in the introduction. For the ones of you who are not familiar with Hernknecht, we are located in the southwestern part of Germany, the Upper Rhine Valley. It's only a 2-hour drive by car to Schwanau. By the way, in Germany, you can drive with a Porsche as fast as you want, not like in Switzerland. So you can break it down to 1.5 hours if you like to, depending on the day. Anyway, just joking. We were founded in 1977 by Martin Hernknecht, who is still running the operation. 45 years later, we have 5,000 people worldwide. We are having a turnover of 1.2 billion euro. We have manufacturing facility in Germany, but also in China and Thailand, India. At the moment, Asia is very dominant in infrastructure for subway and urban development. We are currently divided in 6 major divisions. Traffic handling is the biggest one. Of course, the bigger the machines, the more turnover is involved. We have a mining division since 2000, exploration, going geothermal. That was our initiator in 2000. Unfortunately, we had some failures with Staufen, some cracking. So the geothermal hype at the beginning was going steeply down and diminished, but now it's regenerated with our energy crisis. So we need to tap into the soil as a geothermal energy source. We have the equipment and look forward to it and believe in it. That's a viable option. Then we have on the bottom left side the utility tunneling. I want to focus today a little bit. We also are in the pipeline business and shaft foundations, which I also have some slides about. That's just a little cross-section. So we are driven by the industry, by owners, engineers, contractors, who are asking for a certain type of equipment technologies to help them install do installation in a very environmental and safe manner. And labor is also a big topic at the moment. Automation, digitalization is where we are, robotics, constantly working on in order to make our technologies smarter, as it's called nowadays. Up to now, we have more than 1,200 TBMs for traffic tunneling, more than 2,000 on the utility tunneling side. That's the product portfolio on the utility tunnel. On the left side, that's the micro-tunneling and pipe checking equipment. The new one are called e-power pipe, or direct pipe and pipe express. Of course, HDD is also around since the 1970s, horizontal erection and drilling, big market, big applications. And on the bottom sections, you have also the classic tunnel boring machines, the part phase excavation and the full phase. As you probably know, Switzerland is a tunneling nation. You are fantastic tunnelers in perfect shape. You have done a world record with the Gotthard-based tunnel, 57 kilometers, the world's longest railway tunnel. We were lucky enough to supply 4 machines to do the installations. It was really a challenge to go underneath the Gotthard-based tunnel with 2,000 meters of overburden with really challenging ground conditions. Let's go back to pipe checking. And I started 25 years on the big tunneling side, and the biggest tunnel boring machine at that time was 14.2 meters. For a tunnel in Hamburg. Now we are looking at 17 and bigger diameter, 17 meter and bigger diameter tunnels. So the trend goes to larger diameters, longer distances, deeper alignments, more curves. So you have so much stuff in the ground, you have to go around, you have to steer around. but also some shallow application in an urban environment, because the ground in a downtown area is already so congested with existing structures that it's getting tough to find a space for your additional installations. And if you can imagine, you go longer distance, larger diameters, the type of ground the machine needs to handle is much more complex. If we go deeper, we have hydrostatic water level. We have heard in the morning with the Lake Mead project, 140 meters below the ground, or we are talking about 400 meters now, or 500 is 50 bar. Crazy. I don't know, are you scuba diving? So if you try to go scuba diving, so up to 20 meters, 25 meters, it's okay, yeah? But below 25, 30 meters, you need a tire mix. So your health is really at risk, and that's only done by professionals. And when we talk about 500 meters, I'm not sure. So we need robotics. I think it's not human anymore. But it can be done, definitely, don't get me wrong. And that's why we are relying on those projects to push the envelope. Okay, this gives us another vision to accomplish in the next whatever years. Sorry, a sidetrack here. So back to pipe checking. Pipe checking is very popular around 40 years. You have a launch shaft and a reception shaft, beneficial in urban environment. That's where it's needed because it's minimum interruption on the surface. You have a checking frame in the shaft. You have a thrust block. The shaft needs to be embedded in the ground that you don't get deformations. If you have deformations in your shaft, you cannot operate and steer the machine properly because your guidance systems get weird. So once you have installed everything and you launch the machine, you lower it, you extend your thrust cylinders, and important is also a seal. Everything needs to go through a seal here to avoid that you flood the shaft here. This type of machine is a slurry machine, which is the most popular one. You have feed and discharge line. We are using a bentonite slurry to transport the cuttings, the excavated material back to the surface. And of course, that's what we all know, yeah? We are dealing with the ground. We are dealing with all kind of mixed ground, hard rock, whatever. Nobody knows. So nobody has a crystal ball. We do some investigations, but everything in between is kind of uncertain areas, some kind of speculation. So the ground is the boss for trenchless installations. It decides what type of machine, what type of tools, etc., and that's governing the success and failure of your operation. So on the left side, you see the pipe checking machine operating. So depending on the ground condition, you equip with appropriate tools. So the tools crack the material down in front of the cutting wheel until it's small enough to fit through these openings of your cutting wheel. See the openings. So all the material needs to go through these openings. And in pipe checking, you have a conical crusher chamber, which is acting like a coffee grinder. You're grinding down the material until it's small enough to fit through these openings on the invert. So it's a conical crusher chamber, and all the material goes through here. And whenever it passes here, it's caught up by the discharge line. So the green line, the discharge line, pumps it to the surface. You have a separation plant, shakers on the surface where you just separate the bentonite slurry from the soil. And then the clean bentonite is recirculated into the excavation chamber. So basically you are pumping slurry in a loop. You're adding soil in the excavation chamber and are removing on the surface. Very simple. Now this technology works for smallest machine of 300, 400 millimeter, and exactly the same technology is used by 17, 80 meter machines, just at a bigger scale. Depending on soil formation, rock conditions, whatever, you pick the appropriate cutting wheel. You have the rock cutting wheel on top here, the soft ground, different opening ratio, and the most popular is the one in the middle because it's a mixed soil cutting wheel. So you have a certain guarantee, you have the appropriate equipment, tools on board, depending on what kind of ground conditions you're in. So it's a little bit more on the safe side, but also has some disadvantages. And you see on the left side the AVN technologies, that stands for slurry microtunneling, or mix shield on the bigger machine, that has the widest range. So if you pick an AVN machine, you don't need to worry about what kind of ground conditions you are in. You are safe. Whereas in EPB, you're limited, like HDD, EPB, same. You have to have a certain cohesivity in the ground. You need the clays to silts in order to make this technology work. And that's also shown here, the AVND, the AVN and the AVND. AVND is just an extension where you have another chamber behind the excavation chamber, the working chamber filled with bentonite and air bubble, which sensitively controls the tunnel phase. Because mechanized tunneling is all about advancing the machine, installing the liner by not disturbing the tunnel phase. That's a key. And if you have a slurry type machine, the bentonite slurry stabilizes the tunnel phase in a very homogeneous, sensitive way. The pressure rating is 3 bar. It's very low. That's a standard machine, but the standard application in an urban environment is 30-meter depth. That's typical. On the small diameter side, we can go up to 10 bars. That's a limit at the moment. As we talk about pipe checking versus the big tunnels, in the big tunnels you install the liner and advance the machine. Here you have to push the whole pipe string, not just the machine. The whole pipe string needs to move. And that's why I was so excited when I switched from big tunneling to the smaller equipment. First of all, you need to have all equipment to operate the machine needs to fit in a much smaller space, cross-section. And in addition, you have to move the whole pipe string. So the whole pipe string needs to be equipped with sort of tools to make sure you make it from A to B. The longest pipe checking, the world record in pipe checking is 2.5 kilometers. It was the Europipe tunnel back in 1994. Now you will ask yourself, why is this still the world record? We have 2023, 1994. It's like a forever distance. But there's a certain distance where pipe checking is not economical anymore. Since you have to move the whole pipe string for 2.5 kilometers, imagine how much force you have, frictional loads around the pipe. It's smarter, more economical to switch to segment liner operation where you only push the machine or not the whole tunnel and the whole line anymore. Important for pipe checking, and that's a lifeline, is to lubricate the pipe around. So the machine is excavating, has an overcut, so the machine excavates a bigger hole than the pipe is, and this overcut is filled with a bentonite lubricant. Not the bentonite slurry. The bentonite slurry transports the cuttings, stabilizes the tunnel phase, but the bentonite lubricant is a lubrication. It's around the pipe and fills this 100%, maybe 110, 120%. The 20% additional, that's where the bentonite goes into the pores of the surrounding ground and generates a fantastic lubricant. And that way you can go 2.5 kilometers with not interruption, best case. Okay? So bentonite lubrication is very, very important to make sure your frictional loads are minimized and you can make it from A to B, whatever distance you're looking at. And in case you get stuck, you can split. You have intermediate checking stations involved. That's here. That's a ring of hydraulic cylinders sitting next to between two pipes. And you can activate the cylinders. So you're only pushing the front section and the rear section is not moving. That way you only have to overcome the frictional loads from this intermediate checking station to the machine. So it's much less friction. Okay? So the IGS is a lifeline for you in case your frictional load's getting high because you get some settlements. You have a boulder sitting on your pipe or whatever, yeah? So with the IGSs, you just can make it because you cannot revert the operation. You cannot go backwards. You have to make it to the shaft. Or worst case, get stuck here, then you have to recover the machine or abandon. All right, that's a couple of slides from a job site. Accessibility to the excavation chambers, the smaller the machine was, the more difficult it is to get inside, but it's important because once your tools are gone, especially in the long distance tunnels, the tools are exposed to the wear, right? You have to change them, you have to check them. And that's done from behind the cutting wheel. So all the tools are backloading, so nobody needs to go in front of the cutting wheel. But if you have a machine beside the door, then yeah, you're limited, very, very limited. If you are below the groundwater, We were talking about scuba diving. So it's the same system here. If you want to go into the excavation chamber in the groundwater, you're exposed to the groundwater pressure. So if you're 20 meters down, you're about 2 bars. Okay? So 2 bars diving, not a problem, we learned. But you have to get under the 2-bar compressed air, and that's why you have an airlock on board. Now this is a machine which has a diameter of 1.6 meters, and that's a minimum diameter where you have an airlock, and sit in the airlock, get under compressed air, open the door, get to the front of in the excavation chamber, change tools. Under compressed air conditions, not underwater, under compressed air. So compressed air is basically used to remove the water, to keep the water away from the excavation chamber together with bentonite filter cake, which is generated on the tunnel face. Since we are operated under the groundwater level, we can also operate under the lake, under the river, whatever, or in the lake, in the river, in the ocean. And that's where these offshore or sea outfall technologies has been evolved, I don't know, 15, 20 years, or 10, 15 years ago. So basically you launch your machine onshore, and you do an outfall tunnel into the ocean for storm sewer, or sanitary sewer outfalls, for instance, or desalination plants, and recovers the machine. Once the machine arrives on the predetermined location, you send a diver down, you flood the tunnel, separate the machine from the tunnel, lift the machine up to the surface, as here, bring it to the next harbor, recovers the machine, and get it ready for the next. More applications are, for instance, pipe arch. If you have multiple installations, have a pipe arch and then excavate underneath. Cross passages is a big topic with tunnel safety. So it's the same pipe checking methods, the same technology is used basically to have cross passages, exit or emergency exit between tunnels every 200, 250, 300 meters being used. There are several other methods, but with this technology, this can be done very safely too. Blind hose is also another installation method. This is a project in Mexico, in Gulf of Mexico. There was an oil pipeline installed in the Gulf of Mexico, but the oil needs to be accelerated, needs booster pumps from time to time. So they have the oil pipeline going onshore to the pump station and then back into the ocean, into the Gulf of Mexico, and then continues the journey. Now for this connections under the beaches or outfalls, the contractor, together with the engineers and owners, selected the pipe checking method for a distance of 2.2 kilometers. It's amazing. It's quite a long distance. But in order to be prepared for the unexpected, it's all about tunneling, being prepared for the unexpected, having plan B, plan C, plan D. What happens? What would we do if we get stuck? 2.2 kilometers is a long distance. A lot can happen. And there technology is available where we can convert a pipe checking operation to a segment line operation. But you have to equip the machine properly. So you have basically everything on board for a segment line operation. You have an erector, you have a tailskin, you have gaskets here. And once you get stuck, you don't need to abandon the tunnel. So you have plan B, you convert to a segment line operation and finish the drive, just in case you need it. And in 99% of the cases where you have this kind of push motor scenario, you don't need it. But the 1% where you need it, everybody's so happy to have it installed beforehand. But you need to consider also the size. We talk about very small diameter machines, and it's tough to operate and to work and install the segments. So the minimum we have done is 2 meters in diameter, so whatever size here, to operate segments, build segments. We always recommend to go minimum 2.6 or maybe 3 or 3.6 meters. This is another installation in Israel for a desalination plants, as I said, outfall, recovery, and then bring back the machine. We are trying constantly to push the limits. What are the limits? Distance, diameter, but also curves. How steep can you put your curves, your alignment, your design? And then that also came down to shorter radii. And the one we do are just in progress right now for Asia. Asia is kind of, it's really crazy. They do 90 degrees, whatever. Our steepest now for an Asian project is 60 meters, 60, which is really a big stretch at the moment. Some installation in Switzerland, so of course you have the big mountains. Elevation difference is, if you're a microtunnel from A to B, you most certainly have or most likely have an elevation difference here in Basel for the installation of a cable tunnel. So 60 meters, so this goes to 8 to 15% inclination. And just for these power cables here, it's a bit, which are much smaller than the pipe installed, but it's required to overcome the geology. So back again, the geology is the boss. It determines everything, even the size of the machine. Yeah. Just to install a power cable, you have to install a much bigger diameter pipe there. Anyway, then next is direct pipe, E-power pipe. It's like microtunneling, it's just from surface to surface. You don't need a shaft, you have a steel pipe, you have a pipe thruster clamping a steel pipe, and then push forward, push backward. Push forward, the machine is advancing. Push backward. Why do you want to push backward? So if you have obstruction, if your geotag is not what it's supposed to be, if you have trouble with the machine, if you have, I don't know, tools, you have no tool capacity anymore. And that's why I like this technology very much. It's because it's surface to surface, it's much cheaper than a shaft operation, and you can go backwards. So it's like in your car, you have a rear gear. And as you are pulling back the machine, you inject bentonite into your borehole, and that way stabilize the borehole until you reinsert your machine and finish the drive. Standard pipe checking, no backward going. And the limits again, we are talking about 48 inches, about 1200 millimeter, 2 kilometers, fantastic. Okay? And let me skip E-power pipe because I think I'm running out of time here. It's just for shallow installation, we call it E-power pipe, a very small diameter, 500. For power cable installation, we have the wind farms in the North Sea, we have the industry in the south, so we have to install thousands of kilometers of cables throughout Germany to bring the power where it's needed. Yeah? And that's where the E-power pipe technology is very, very popular. And you have instead of a telescopic checking frame, you have a rack and pinion system where you recover the pipes. You use special pipes for the installation. And then once a machine is on the exit side and dismantles, then you connect your HDPE pipe, which is a casing pipe for the power cable. Then you retract the pipe together with the HDPE pipe and install the conduit pipe for the power cable. And again, 2 kilometers. 2 kilometers, 500 millimeters, it's fantastic, but it only works in sandy soil conditions, like here in the Netherlands. So it doesn't work in any other more difficult soils. Then the last topic is vertical shaft sinking machine. It's a very economic, of course it's economical, but the reason why it's so popular, it became popular, we started in 2004 with the first installation and steps and Jeddah and Kuwait and Russia, whatever. Now it really is taking up because it's beneficial in an urban environment. Guess why? We are all geotechnicians or whatever. If with the installation method, you don't need to lower the groundwater. If you have installation to lower the groundwater, what's happening with your surrounding buildings? They get some settlements, right? Unless you have a proper foundation or is founded on rock or whatever. But whenever you remove the water, you get some settlements, and that's jeopardizing not just the buildings, foundations, whatever. So in an urban environment, a vertical shaft sinking machine, 0 groundwater lowering, because the machine operates under the water level. So you're installing the machine, it's basically a part phase excavation just upside down. This kind of technology can be used on horizontal, but here it's used for shaft installation. You're again pumping here water, you don't need a bentonite slurry, you don't have a tunnel face to stabilize, so it's just the water, the groundwater. You excavate, and then you pump the material to the separation plant up there, and then the clean water goes back into the shaft. So no balance, no interaction with the water level, not too much. And the shaft is held in place by string checks, the weight of the shaft. Here, string check 1, 2, 3. The whole shaft together with the machine is held in place until you are finished. So once your shaft is installed, you are at a certain depth, Then you install the reinforcement, you pour a Dremel block, concrete, and another concrete layer, and whatever, until it's stable enough, and then, in the last stage, you remove the water. So your interaction with the surrounding ground is minimized, so no risk or little risk of settlements around. Different type of diameters, shaft diameters for different applications require different size machines. So the VSM 9000 is for 9-meter shaft, 12-meter, 50-meter, 80-meter shafts. We're also talking about twin arms on the bigger ones for 23, 25, wherever the development goes. It's constantly, every year, pushing the limits, getting bigger and longer and larger. Application of ventilation shafts for existing tunnels, launch and reception shafts for rear tunnels, and the most popular, not popular, the exciting one at the moment is underground car parking systems. How tough it is to get a proper parking spot in an urban environment. How much do you have to pay for it? How much is an urban environment a real estate cost? And why don't we put all the cars under the buildings and becoming part of their structure? Well, the limitation at the moment is 10 bar is about 100 meter shaft depths, and of course the geology, depending on the tools, we have some limitations. Every technology has it. We are at about 140 MPa. One is a big project last year, or the previous years, was the Grand Paris project in Paris, and see how small the footprint is, where you can install the shaft in a really tight spot with minimum noise, minimum dust and whatever, and save minimum risk of settlements. So 45 meters or 35 times 80 meters, that's enough where you can install. Look at this in Spain, that were one of the first projects. The distance between the houses was 12 meters. And it was a ventilation shaft for a subway underneath. I already indicated underground car parking, different size. The bigger the diameter, the more cars we can create space for this underground car parking system. Basically, you put it in a garage, go shopping, come back, your car stands there and comes out of a system and recognizes where you are. It's the first installation in China. In China, there are many more of these projects being planned as part of the infrastructure projects. All right, that's it. Thank you.
Thank you very much for the interesting presentation. Are there any questions? We have only a couple of minutes because we have some delay. Please.
No.
A misunderstanding. Yeah, there is one.
Thank you very much. For pipe jacking, if we want to pipe jack on a curve line, is it possible to control the eccentricity? Because we apply the force, the thrust force, at the beginning of the line, and on the curve we will have eccentricity with that. And with the possibility of having, in a perfect case, bentonite can be all around. But if we have some kind of dissymmetry left and right, we may have important eccentricity. Is there a way to control that, to monitor that, or to reduce that? Yeah, thank you.
Yeah, it can be done. It's the market leader on this kind of technology is based in Switzerland. It was a PhD student from ETH here. It's called Check Control. The company was founded, I don't know, 8-10 years ago. They have a hydraulic joint. And it's basically between the pipe joints, because the pipeline is always following the machine into the excavation to the area. It's following the path of the least resistance. Okay? And between the joints, as in the joint between the pipes, there's a hydraulic hose. Normally you use a wooden packer because you have an extra eccentric load. So you have on the left side a little bit more load than on the right side, giving you the eccentricity. if you have a hydraulic hose in between, the fluid in the hose is displaced from the area where you have a higher compression to the area where you have less compression. That way, utilizing the capacity to transfer the loads very nicely, very evenly. So the hydraulic joint, the hose, is much better than a wooden packer. And they are measuring the distances. They're measuring the gap and the load with the hydraulic.
Probably the problem with jack control is that, yeah, you have the same pressure all around, but not necessarily the same stiffness. Because when you turn around like this, here is much more compressed, internal side.
Yeah.
And in the external side, it's less compressed. And the stiffness changes with the deformation.
Right.
And this will add up to the eccentricity, actually. It's a good thing to monitor, but not necessarily to reduce the eccentricity. You know what I mean?
Yeah, I totally understand.
We have.
Right.
Yeah.
Yeah, and with the eccentricity, you get a certain moment, and you get a lateral force. And this lateral force is affected or counterbalanced by the soil. So the pipe is strong in the axial direction, but it's not so strong in the radial direction. And that's why, and at the end of the day, you want to have a pipeline without cracks. During the installation, you would have to avoid the cracks. That's why the hydraulic joints is minimum or reducing the electricity to whatever, eccentricity, not
eccentricity.
Eccentricity to almost zero. With a wooden packer, you always have, of course, you have much more loads here than there. And then you can calculate the eccentricity easily. With a uniform pressure distribution with the hydraulics, if you have uniform distribution, you get a little lateral forces, but that pipe is with a bentonite lubrication around minimal, the effect on the pipes, the negative effect is minimized there. But still there is one. Check control can answer the question much better. They have all the data in their system, they're measuring the gaps, they're measuring the loads, they can calculate the eccentricity in their system.
Thank you.
So, thank you very much. We don't
Thank you.